So my presentation is on the birthday paradox, and it kind of focuses on how special your birthday is, how likely it is that you share a birthday in a room with other people. So it's your birthday, but how really special is that? So if we use the pigeonhole principle, for the probability of two people to have the same of something to be 100%, the number of people must be greater than the number of possibilities. So the probability equals 100% if and only if the number of people is greater than the number of possibilities. Using this principle, there would need to be 366 people in a group for there to be a 100% chance for there to be a repeat birthday, because there are 365 possible birthdays. But the probability theory tells us that chances change exponentially, not linearly. Anyone can be in a match with anyone. You don't have to be involved in the match. The person's point of view, they're only matching with 22 people in a room of 23. But there's actually much more comparisons being taking place between others. So the probability that two people have the same birthdays, 364 over 365, or 0.997. However, if we raise this number to 253, which is the number of comparisons that occur with 23 people in the room, this probability comes out to be just below 0.5 or 0.4995. This means that in a room of 23, it is more likely than not that two people have the same birthday. Also, if the original probability of two people, 0.997, is used with 70 people, there ends up being a 99.9% chance that two people share a birthday in the room. So comparing the 365 to the 70, there needs to be much less using the probability theory for there to be a repeat birthday. So why do humans not really think this way? Why do humans think there needs to be much more for there to be a repeat birthday? Well, many times humans see the probability of something happening as being the same of the probability of happening once divided by the number of trials you want to do. But this is incorrect. It should actually be the probability of happening once to the power of the number of trials that you want to do. And this comes out to be much lower than the divided. It drops much faster when you do the exponent. So also in a room with 23 people look at the problem as themselves comparing to 22 others, but they don't see that there are actually 253 comparisons being made between other people. So this number can be solved taking the number of people times the number of people minus 1 divided by 2, or adding up all the numbers less than the number of people. So this in math would be 23 times 22 divided by 2, or all the numbers lower than 23 added up, and it reaches 253 both times. So this graph shows dividing to solve probability versus doing exponent to solve for the power using heads or tails. So dividing the chance by the number of trials, you see this drops much slower, and doesn't reach 0 as fast as the exponentially decreasing chances, which are the correct thing. So this means that when it drops, the exponentially drops much faster, meaning that the probability would drop much faster, meaning that the probability of two people sharing a birthday would actually increase, because what we're solving for is the probability of people not sharing a birthday. So this really means that there needs to be less people than you think for two people in a room to share a birthday. So next time you're in a class with more than 30 people, think about, you're more than likely to share a birthday with someone in the room. Just find that out. Well, have a good rest of your day. Thank you.